Hey guys, in this video we are going to talk about a really cool topic, magnetic flux. Flux is a lot like flow, though we want to remind ourselves that magnetic field lines do not flow. They are simply vectors that indicate a direction and a magnitude. But the magnetic field itself is not moving. However, you can calculate the amount of them in a given space, and that is the flux. So the flux is defined as the amount of field lines moving through a given area. You can almost think of it as how much water is flowing through a tube. Though, again, reminding yourself that magnetic field lines do not flow, they are simply vectors. You can think of it perhaps as visualizing them as flowing wouldn't be too off if you took a snapshot of water flowing and you calculated all the vectors of the arrows of the water molecules and all of them moving perpendicularly through an area. That would be a cool way of visualizing it. So for instance, if I have a little circle here and I have field lines moving through it, the amount of field lines and the strength of those field lines moving through the area is the flux. So how do we calculate flux? By the way, we use the Greek letter phi. This is the flux, and it simply is the field strength times the area that the field lines are running through. Now we do want the field to go through the area, so therefore we want it to be perpendicular. For instance, if I had an area here and the field were not running through it but were perpendicular to it, meaning it's running in the same plane, so this is not going through the circle, it's running in the same plane as it. Maybe I can draw that a little differently. Let's draw a horizontal circle here. So this is a horizontal circle, and the field line is simply going along the circle. So it's not going through the circle. If it's not going through the circle, then the flux is 0. So if nothing's flowing through it, if nothing's pointing through it, then the field would be 0. Here you want the field lines to go through the hoop. Let's draw field lines in a different way. Let's say we have x's. X's, of course, meaning into the screen or the page. And let's say that I want to know the flux through different areas. I'm going to draw a whole bunch. So don't worry, you're only going to have to do this conceptually and mathematically. You're not necessarily going to have to draw and count x's. Let's say I have a small and a big circle. Let's say this is area A1 and this is area A2. Which has more flux? Well, I think it makes tons of sense that this one has more flux, that the flux of area A1 is simply the magnetic field times A1, and the flux of A2 is simply the magnetic field times A2. You can imagine these field lines going into the page, through the loop, so the more area you have, the more field you have. Sorry, more flux, the more field lines flowing through the area you have. So therefore, the more flux you have. I love that word flux. How many field lines are moving through the area? So keep in mind that the more field lines you have per area is the strength of the field. So that's why obviously if you have stronger field lines, you're going to have more flux too. Just like if you had more water flowing in the same pipe of the same area, you'd have more flow. Similar idea. Cool. So this is the idea of flux. Let's do a calculation example, and then in the next video we will talk about current generation by changing flux. So my little example here, I'm just going to make up a number. Let's say I have a square loop of current of side 2 meters. And the current is, or let's say that I don't know the current. We don't need to know the current. What I do need to know is how big this square is, and of course how strong the field is. Let's say we have a uniform field going into the square, which has a field strength of 4 Tesla. Then of course the flux will simply be the field times the area, which will be 4 Tesla times, careful, the area of a square is 4 square meters if the side is 2, so that of course is 16 Tesla meters squared. There's no special unit for flux, it's just field times area. If I were to reduce the side by a factor of 2, and I have the same field, what does that do to the flux? So we'll call this flux 1. This is the area 1. This is area 2. Saying proportionately, the side went down by a factor of 2, therefore the area went down by a factor of 4. So you can also confirm that. The area will be only 1 square meter, so we have 4 Tesla times 1 square meter, of course, will be 4 Tesla meters squared. Easy done. So stay tuned to the next video. Be very careful to try to keep this easy, that it's simply the amount of the field, the strength of the field, times the area. So next we're going to keep in mind direction. Direction of field is going to, and direction of flux is going to make a huge difference. So it's going to get a little weird, guys, but it's going to be great. Don't you worry. Alright, cool. I'll see you in the next video.